and welcome to the New York City Category Theory Seminar. Today is December 2nd, 2020, and Andrew Winkler is going to tell us about functors as homomorphisms of quivered algebras. Andrew, to start off by telling us a little bit about yourself.
Let's see. So I was a student of Peter Lack's and then spent some time at Stanford and Columbia on the faculty, and then started a company which completely derailed me. And I've been in industry ever since, but never lost interest in mathematical things. So this is some stuff I've been exploring over the last number of years.
Nice. Well, welcome. Okay,
Thank you.
go.
So the first thing to say is that nothing I'm going to talk about is terribly complicated. So if anything is unclear, the fault is entirely in the exposition. So please, by all means, speak up and make me clarify. As I say, the ideas are quite simple, but there's a certain beauty in that simplicity, I find. So hopefully you'll enjoy it too. So first of all, we want to talk about quivers. And formally, a quiver is an algebra that's defined by two unary operators and two equations. And so it's convenient to use the same symbol for both operators and simply use a prefix and a postfix notation. So a pre-star A is one operation and a post-star A is another, where A is an element of this quiver. In ordinary English, a quiver, of course, is something that holds arrows. So that's the picture here, is that we think of arrows as belonging to a quiver. And these operations, in a way that we'll see, define arrows for us.
I thought a usual definition of a quiver is a finite bunch of arrows. Or is there a finiteness condition here?
There's not.
Okay, and what is A to the left star, A to the right star? What arrow is it? Does it form a graph of some sort?
The effect of these operations, as I'll show you in a second, is it essentially defines a directed multigraph in an algebraic way.
Okay, so you're going to show us pictures.
Yes.
Good.
In fact, let me go ahead and do that a second. So if I stop that share for a second and start this one. So you can think of A as an arrow, and then you can think of, it actually turns out you can either think of left star A as where the arrow starts and right star A where the arrow ends. You can equally well think of it the other way around. The mathematics is completely right-left symmetric, and so couldn't care less how you choose to interpret it. And so you can think of this as kind of an arrows-only way of defining a graph. So vertices are themselves arrows of a particular type. And
you can define categories without using the word objects.
Yes, the arrows only definition of a category is kind of in a similar vein.
Right. And
that'll actually come up as a part of this too. So with all algebras, we have an idea of homomorphism, namely they're maps that commute with the operations. And so that's the concept of homomorphism here. And again, the axioms are completely right-left symmetric, so that imposes a duality where the opposite of any true statement is also true. And so the first equation here simply says that if anything in the image of the left star operator is fixed by the right star operator, and anything in the image of the right star operator is fixed by the left star operator. So some examples, this one is very much a directed graph kind of thing. You just consider pairs, A, B, and you define your operations to form a pair having two equal components, either taken from the right or taken from the left. And so if you think of A or B as being a vertex, then we're identifying the pair AA as the vertex rather than A itself, so that, again, vertices become simply arrows like edges. We can extend this by also inserting a relation. A and B, of course, are sets, whether we, in the usual foundations, whether we're thinking of them as that or not. And so R is simply a relation from A to B. And it has, for its star operators, we simply take the diagonal relation on the common right element or left element that we pick out. And the equations are defined because it's clear that if I take a star operation on something like this, I'm just going to get it back again. Of course, the most interesting example for our purposes is that of a category. And here, the star operation simply is we take an arrow A, we extract its domain, and then we, in turn, form the identity on that domain in a two-typed way of thinking about categories. In an arrows-only way of thinking about categories, of course, the domain is the identity. But in any event, that gives us two operations. And identities, of course, have the same domain and codomain. And so the star operations on them will just reproduce themselves on either side. And again, the structure doesn't really care about left or right, so we could equally well define it in the opposite way. And then the first thing to notice is that a functor is a, this defines a quiver structure. We have the two necessary operators. We also have the equation satisfied because if we start with an identity and we take its domain or its codomain and we then ask for the identity on that, we're back to the identity we started with. So the first thing to notice is that if we have a functor, then it is a homomorphism for this quiver structure, as well as, of course, for the binary composition that defines a category. And in fact, that's exactly what a functor is a map which is a homomorphism for those two different algebraic structures.
One second.
Okay.
A functor usually has to preserve composition.
Yes, that's the binary.
Right, but you don't, homomorphisms of quivers, take a quiver as a special type of category, or is the other way around?
No, it's a special type of algebra. And so there's a concept of homomorphism for any kind of algebra.
Right.
And so,
so go on. So a map is a functor if and only if it's a homomorphism for this quiver algebra structure. A functor usually preserves composition, and I don't see how you're going to get composition here.
And also homomorphism for the binary composition.
Oh, okay. The if and only if is and. I definitely. Okay, sorry. Perfect.
Yeah, I need parentheses, I guess, here or something.
Right.
So
the comma, you just need to take out that comma. Perfect, sorry.
Sorry, okay. So a first thing to notice is about this algebraic structure is that the unary operators are both idempotent. And the way to see that is you simply form a triple expression and then you reduce it in the two possible ways. You can use the axioms to eliminate this star and then eliminate this star, which would give you the right side. But you can also use the axioms to eliminate this star, which would leave you with the left side. And of course, the same thing is true in the other direction. And a good definition is supposed to be an equivalence. So we have an equivalence, and this is what defines a vertex. If A is its own image under the right star operation, then clearly there's some B for which it's the right star image. And, but if this is true, if we apply the left star operator, that will just give us a B star on the right, which is A again. So we get this equation. If this is true, then certainly there's a B for which A is in the image of star B. But if that's true, if we apply the right star image to this, then on the right side, we get this. On the left side, we get B left star again, which is just A, which gives us the left side. So these are all equivalent, and these define a vertex. And so by an edge, we mean simply anything that's not a vertex. And we can capture all of these by simply forming a class of vertices, forming classes of arrows for those two vertices, with A left star being U, A right star being V. And the only constraints are that U is in its own such collection, and all these collections are disjoint. So the next thing we want to bring into the picture is a binary partial algebra. And the binary algebra part means that we can compose two things to get something back in the algebra. And we'll just write that by juxtaposing, possibly surrounding by parentheses, but wherever we can do so without ambiguity, we'll drop those parentheses. The key part is the partial part, which is that it need not be the case that this is defined for all possible pairs. And certainly in the case of a category, unless you have a monoid, it's not going to be true that any two arrows can be composed. There will be a condition that has to be satisfied for the composition to be defined. And in fact, it's even possible that there are no pairs whose compositions are defined at all. So it's just a map with a given codomain A, and instead of the domain being A cross A, as it would be for a binary algebra, it's simply anything contained in it. And here, of course, we have a notion of homomorphism, but it's a bit more subtle than it is for algebras because of the fact that there's the possibility that a composition fails to be defined. So the obvious condition is that if you have A having image A prime and B having image B prime, then the image of AB should be the image of A prime B prime. But that condition alone doesn't give you a well-behaved notion. You need some sort of implication having to do with the existence of compositions. And the one that's useful for us today is that if the composition exists in the domain, then the composition of the images also exists. But it turns out the reflexive version, where you have the images composable, implying that their pre-images are, also gives you a well-defined category of homomorphisms. So some examples. The simplest possible example is if you define your compositions to have as a domain the empty set, so that there are no compositions defined. And so there you just have ordinary sets. Every set has this this completely trivial algebra structure where there are no compositions, but then all maps are homomorphisms in the same way that for every set you also have a discrete category structure, and all the maps there are functors. At kind of the opposite extreme is if all compositions are defined, then you have a binary algebra, or what's here calls a magma. with the usual algebra concept of homomorphisms. And semigroups are an example of such things. And of course, categories, where if you would have a functor, it is a homomorphism, but there certainly can be homomorphisms that are not functors. A really simple example of that is if you take a monoid and consider it as a semigroup and then adjoin to it a unit, the inclusion is clearly a homomorphism, but of course not a functor. And we've already said this, again, functors are exactly the things that are both homomorphisms for this binary structure and also for the quiver structure. Now, if I have a quiver, I can also define a binary partial algebra by simply saying, I'll define AB when A is pre-star B, and in that case, I define the composition to just be B. I'll also define it if A right star is B, and in which case the composition is defined to be A. And as simple as this is, it has some interesting structure, right? Or at least some pretty structure. But the first thing is we have to know that it's well defined. And to see that, we have to consider the possibility that both of these conditions are true, in which case it had better be true that A is equal to B for it to be well defined. But that's fine, because if we have both of those equations, then if I apply a right star to this, I'll get that B star is A star. If I apply a right star here, I get that B is B star, but then B is A. And so the composition is that common value. Now, all of these algebras satisfy an axiom of balance, which is that if I can form one triple product, then I can also form the other triple product. And so it's an if and only if. This is certainly a familiar fact for categories. In the case of magmas, all compositions are defined, so it's trivially true. Similarly, if no compositions are defined, it's also equally trivially true. It's true for the algebra we just described, and also true for, since it's true of magmas, it's also true for things like loops and quasi-groups. And so it turns out that the structural theory here kind of spawns off all kinds of interesting chunks of mathematics.
The composition is not associative. It just whether the question is whether it exists or not. Whether
exactly.
So they can both be defined but not equal.
They need not be equal. That's correct. And in loops and quasi-groups, they're not, generally speaking. Although the case where they are equal is, of course, of particular interest, and we'll get to that in a second. But before we do, we can, of course, split the if and only if into its two constituent pieces. But we can also break each of those down further into constituent parts, each one of which has an interesting connection with certain ideals. So by an ideal, we simply mean a subset that is closed under multiplication from the outside. A left ideal under multiplication from the left, a right ideal from the right, or a two-sided ideal. You're probably used to thinking of ideals in the context of, say, rings, where there's also an additive structure. But it turns out to make perfectly good sense to sort of think of it in the absence of that additive structure. And so the way it works is, the first axiom says essentially that if I take some arrow C or element C, I should say. It's not really useful to think of them yet as arrows. So I apologize for my typo here. I should be saying elements here, but at any rate, I take an element C and I look at the things that can't be composed with it on its right. And that forms a left ideal. That's essentially the content of this axiom. If that isn't immediately apparent, a way to make it more apparent is to rewrite this by saying, if BC is not defined, then ABC is also not defined. So if B is in the ideal, then AB is in the ideal, which is what you mean by an ideal, by a left ideal. And the other corresponding axiom has the exact same interpretation in the opposite direction. The next ones define ideals in terms of units. So first of all, let me define a left unit to be something that satisfies, if I can compose it with something, say A to the left, then I just get A back. And similarly, a right unit, if I can compose on the right, if I get the same thing back, that defines a right unit. And so if I start with a left unit and look at all the things that can be composed to the right of the left unit, or which is to say, having the unit on the left, will form a right ideal. That's not equivalent to this axiom, but it's an immediate implication of it. And similarly on the other side. So there's a kind of a motif all over mathematics where if you have things like ideals, you can do two things. One is you can start to explore structure to kind of try to decompose and understand the structure you're facing. But also interesting things happen if you impose a triviality condition on those ideals. For example, if you have a ring that has no principal ideals, it's a division ring, or in the commutative case, a field. In a somewhat similar vein, if you have a group that doesn't have any normal subgroups, you have a simple group. And the triviality of these component structures turn out often to be very interesting axioms characterizing interesting structures. And something like that happens here. So first of all, if I take these ideals of non-composability and force them to be trivial by being empty, then I force all pairs to be composable. And that's exactly a magma. So we saw magmas as examples of these binary partial, or these balanced algebras, but this exhibits them as essentially components of them, as sort of one of the atoms in the structure theory of these things. So if we take the opposite direction by making these ideals trivial in the sense that they are everything, then instead of forcing all pairs to be composable, the opposite happens, and we force no pairs to be composable. And that gives us the bare algebras, which essentially are just sets. But again, rather than appearing as examples, now they appear as part of the structure theory. And of course, when in addition to being balanced, the two sides are actually equal, we have an associativity property. These are a particularly kind of rich mathematical structure because for one thing, there are like a dozen different equivalent characterizations of them. One of which is if I form any expression tree with k leaves, I can rebalance that tree in arbitrary ways. And if this axiom holds, then all of them, if one of them can be evaluated, then all of them can be evaluated, and they all evaluate to the same thing, which is the familiar form of the sort of general property of associativity that you get by induction in groups and semigroups and so on, except that even in this partially defined context, it holds. Another way of getting them is if you take an arbitrary semigroup and you take an ideal in the semigroup, if you excise it, then you end up with one of these associations where the associativity property holds. Another way of thinking about them is if I think of this as being a property of B, and I take an algebra that doesn't necessarily satisfy these axioms, but if I focus on the B's for which this is true for all A and C, then if I call those associators, then they in fact form a subalgebra. And so these become a structural component of in the general case in any event. And this axiom turns out it's not precisely what you need, but it's certainly sufficient for and is rather close to what you need for principal ideals to in fact be ideals. And again, you know, forcing ideals to be trivial gives you strong, it kind of carves out pieces of mathematics as we've discussed. So one ideal whose triviality has some really interesting implications is if we take all the left units, we have those ideals that are all the things that are composable with it. If I take the union of that, if that ideal is trivial because it's everything, we'll call it left quivered for reasons that will become apparent in a moment. And similarly, on the right side. And it's quivered if it's both left and right quivered. So let's talk for a second about what that means. It means every element can be composed on its left with a left unit, and every element can also be composed on its right with a right unit. But now something fun happens, which is, in particular, every left unit can be composed on its right with a right unit, and every right unit can be composed on its left with a left unit. But if I take a left unit and a right unit and I can compose them, then in fact they have to be equal. Because if UV is defined, if U is a left unit, then this has to be V, but if V is a right unit, it has to be U, so they have to be equal. And so that means every left unit is also a right unit and vice versa. And in fact, if I have some left unit composable with A, it exists, but it's also unique. Because if any two units could both be composed with A, I can force them to be composable with each other, which forces them to be equal. And that creates a quiver structure. I define the left star of A to be that unique unit composable with A on its left, and A right star to be that unique unit that's composable with A on its right. And so we defined an example of an algebra structure from a quiver. If starting from a quivered algebra, we form the quiver structure and then look at the composition in the that's defined by that quiver structure, it's what we started with. Because A left star A is equal to A, that is both true because A star is by definition the unit composable with A, but it's also true because we defined this to be true if we started from a quiver. So those two constructions agree. And of course, there are functors in an adjunction lying around here, as you would imagine. But before we get to that, let's come back to categories and see how they kind of fit into this quivered association picture. So first of all, a category clearly is a quivered association. Every arrow is composable with an identity on its left and an identity on its right. and is clearly associative. But there's one extra piece that makes it a category, and that actually turns out also to be defined by the triviality of an ideal. In this case, if you consider the elements that that cause triple products to be formed from binary compositions. So I have an element B, and if AB is defined and BC is defined, so let me back up a second and remind you, in a category, if AB is defined, then that means that the domain and codomain match up. And if BC is defined, then again, the domain and the codomain match up. But then that forces the triple products to exist because the domain and codomain of the compositions are simply those of their constituent pieces. Now, in an arbitrary association, these gregarious elements form an ideal. And so again, we can ask what happens if they're totally trivial. In the world of quivered associations, that precisely characterizes categories. And this game we can continue to play if we, in a category, consider the ideal of non-left or non-right invertible elements. If that's forced to be trivial, then that precisely defines a groupoid. If we combine that with the magma condition, we have a group. Rings arise similarly, and so on. Now, going back to our the algebra we formed from a quiver, if we have a vertex A, so that A is equal to its right star, then A can be composed with A because it's the same thing as A star, and that's A, so all the vertices are idempotent. The vertices are moreover limit, or excuse me, are units. If we have a composition AB, then there were two cases. One possibility was that A was the left star of B, and one was that B was the right star of A. And in this first case, the composition was defined to be B. But if A is a vertex, in the second case, A is equal to B, because A is equal to A right star if A is a vertex. So A is equal to B. And so AB is the same thing as AA, which is the same thing as A, which is the same thing as B. So in both cases, we get AB as B. And so that means A is a left unit. But vertex is a self-dual concept, so that means it's also a right unit. So the entire algebra, it has a very simple structure. If we imagine an arbitrary expression, then one possibility is that there is an edge in the tree somewhere. And if that's so, then inductively it forces everything to its left to be an A left star and everything to its right to be an A right star. And so the whole tree evaluates to just being A. If it has no edges, then it has to have at least one vertex. And again, inductively, all of the other leaves must be that same vertex, and the entire expression simply reduces to that. There's one more notion that we need, which is related to the notion of prime number, but at a level of units as opposed to isomorphisms. And that is, we'll call it strongly reducible if whenever we have a product, then either the left constituent is a left unit or the right constituent is a right unit. And so, of course, the other one is simply C itself. Mentioned in passing, this notion is precisely what's at the root of binary search. And so, independently of the context here, there's some interest in the notion. So this construction of an algebra from a quiver is functorial. If we have a quiver homomorphism, then I claim it's also a homomorphism of the binary partial algebra. Namely, if I have a composable pair AB, then their images are also composable and match up. And the two cases are similar. One case is that A is B star, so AB is B. And then, so if I apply my homomorphism to both sides, that I have this equation. But because it's a quiver homomorphism, it commutes with the star action, so I get that. But then this tells me that A prime can be composed with B prime and gives B prime as a result. Going in the other direction is where the strong irreducibility comes in. If I have a homomorphism of these binary partial algebras, of these quivered algebras, then I start with A and form the product A star, which is A. And then that implies that the images can be composed. And so I compose them and they have to have the compatibility matching. That's just the definition of homomorphism there. But since this is strongly irreducible, either this is a unit or this is a unit. So we have two cases to consider. If this is a unit, then in fact, it must be the unit with which A phi is composable, namely this, and we have the quiver homomorphism property satisfied. On the other hand, if we have A phi being a unit, then a unit composed with this just gives it this as this again, so we obtain that A star phi is equal to A phi. But since A phi is a unit, that's the same thing as A phi right star, and so again we have the quiver homomorphism property. And on the opposite side, of course, it's the exact same dual argument. We, in fact, have an adjunction, and the argument is quite similar. If we have a homomorphism from one of these binary algebras to the algebra defined by the quiver Q, then we get a homomorphism from the quiver defined on A into the original quiver Q. And again, from this existing, the homomorphism property guarantees that this also exists. And so again, because of the special structure of this algebra, one of these two equalities has to hold. This forces A phi to be a unit. So then this has to be equal to A phi, which gives us this equality, which in turn, since this is a unit, gives us this equality, and we get the quiver homomorphism property. And again, it's the same on the other side. And on the other hand, if we start out with an algebra which is element-wise strongly irreducible, we form the quiver from it and look at a homomorphism from there into Q, then considered instead as a homomorphism, as a map from A to the algebra from Q, that's also a homomorphism. And the argument is quite similar. all of these simply involve using the unit properties and the definitions to sort out. So the upshot of all of this is that if I start with a quivered association, then I can, by looking at the unit structure, I get a quiver. And then if I start with a quiver, then I can get a quivered association that has this elementwise strongly irreducible property. And so it will coincide with the one I started with if it also has that property. If it doesn't also have that property, then of course it can't coincide with it. But we can kind of think of the original algebra as simultaneously having two compatible algebraic structures, one of which is simply the units and their compositions with everything, and the other is whatever other compositions also happen to exist. And so the upshot of this is that if you have quivered associations, then what you would, in the case of a category, and even more generally, you would like to think of a functor as being something which is, first of all, a homomorphism for the binary structure, but also a homomorphism for the quiver structure. And what we've just seen is that being a homomorphism for the quiver algebra defined by the unary operators is exactly the same as being a homomorphism for the corresponding binary algebra that it induces. And so a functor is a homomorphism for all three of these algebraic structures. But of course, these two are equivalent. There's one more thought here, which is if I take any quivered balanced algebra, if the composition AB exists, then necessarily their units match up. A unit composable with A on the right, by associativity, essentially, let me say associativity, but associativity isn't actually necessary because the units, with units, balance is enough. The associativity is for free. But if I can compose with a unit A, a unit U with A on the right, then also it composes with B on the left, and that forces this equality. And conversely, if it composes with B to its left, it must compose with A on its right, and again, forces this equality. And so the minimal algebraic structure that makes sense with the quiver structure only defines compositions with units. Those are kind of the only ones that have to exist. A maximal one would be one where every composition that can exist does. And so that would be the converse, that if the units match up, then in fact the composition exists. And that's actually the same thing as saying that this common unit satisfies the gregarious property, or is in the gregarious ideal. And so in fact, that maximality property is precisely what distinguishes categories among these quivered associations. Any questions?
Nope. That's it? You're finished?
I think so. I mentioned the abstract something about monads, and I don't think we've got enough time left to delve into that. I did write a blog post on that, which will come up if you search for me and monad. There's a categorical, a computational interpretation of monads, and which express them in kind of several, in terms of several kind of atomic pieces. and then there are connections among them. But those connections kind of split up into two pieces, which I think is reminiscent of the way that categories themselves kind of split up into both a binary algebra piece and also a unit structure piece. And a corresponding thing happens in that computational model.
Is there anything interesting in between the minimal and maximal structure?
The answer is probably yes. But the most, at least as far as I can see, the most interesting mathematics always emerges from having a structural component be trivial. And so the fact that categories are defined, this maximality condition is equivalent to the triviality of that ideal of gregarious elements. Kind of makes, kind of distinguishes categories in this kind of world. And of course, you know, most of mathematics can be thought of in a context of category theory, right? I mean, topology arises very naturally as a topic in category theory. You know, analysis and algebraic geometry arise out of ringed spaces, which are just functors on topologies valued in functors. And you know, so the thing that's kind of curious, I think, is that, you know, as all-encompassing as categories are, there are important mathematical structures like directed graphs, like semigroups, that while clearly connected with category theory, are hard to think of as being sort of subsets of category theory. And so in this larger framework, you know, all of those pieces have a natural place too.
Thank you.
And can I tell you what this reminds me of?
Sure.
My thesis advisor, when he got his degree, he had a postdoc at Harvard, and they gave him to teach real analysis. And he never took real analysis. He never, you know, whatever. But he looked it up, and he was a pretty brilliant guy. And so he started off. He came in the first day and gave the definition of a monad, a monoid. And then a commutative monoid, and then Archimedean monoid, and then a group, and then a cancellatable monoid, and then a group, and then a commutative group, and then a ring, and then an algebra, and then and he got all the way to something called the Petter-Weyl theorem, which is like an advanced whatever, and he never mentioned the word real numbers because he just did it purely algebraic. This is amazing because you know, like, you start off with this simple little structure with these two little, you know, unary operations, and you got so much out of it. It's really amazing. It's very nice.
Thank you. Like I said, I found it beautiful. So if you're able to also get some enjoyment out of it, I'm delighted.
Right. Any questions? Any discussion? If not, let's thank this.
Yeah, so when you first defined the functor, you had to consider that the composition is somehow given externally, right? Not in terms of quivers. And finally, you come to characterization just purely in terms of quivers, right?
Yeah, I mean, I could have simply started with binary partial algebras and gotten to quivers just from considering the unit structure of quivered algebras. But I thought that the exposition that way would be less clear. It seemed like it might be easier to follow by, you know, sort of starting with that sort of simple piece and having that picture in mind.
That's true. Thank you.
Anyways, let's thank our speaker again. And Thank you all. Thank you, Andrew. And next week, we're going to have Dan Scheibler. He's going to talk about functorial, manifold, and overlapping clustering or something. Anyways, but you can look it up on the webpage. Anyways, I hope to see you all then. Everybody all right?
Thank you.
Thank you, Andrew. Thank you.
Yeah, thank you. Bye-bye.
Okay. Take care. Okay. So I'm